In mathematics, a topological ring is a ring R which is also a topological space such that both the addition and the multiplication are continuous as maps R times R, where R times R carries the product topology. General comments. The group of units R times of R is a topological group when endowed with the topology coming from the embedding of R times into the product R times Rs. However, if the unit group is endowed with the subspace topology as a subspace of R, it may not be a topological group, because inversion on R times need not be continuous with respect to the subspace topology. An example of this situation is the ideal ring of a global field. Its unit group, called the ideal group, is not a topological group in the subspace topology. If inversion on R times is continuous in the subspace topology of R, then these two topologies on R times are the same. If one does not require a ring to have a unit, then one has to add the requirement of continuity of the additive inverse, or equivalently, to define the topological ring as a ring which is a topological group in which multiplication is continuous. 2 examples. Topological rings occur in mathematical analysis, for examples as rings of continuous real-valued functions on some topological space, or as rings of continuous linear operators on some normed vector space. All Banach algebras are topological rings. The rational, real, complex and p-adic numbers are also topological rings with their standard topologies. In the plane, split complex numbers and dual numbers form alternative topological rings. See hypercomplex numbers for other low-dimensional examples. In algebra, the following construction is common. One starts with a commutative ring R containing an ideal I, and then considers the I-adic topology on R. A subset U of R is open if and only if for every x in U there exists a natural number n such that x plus in U. This turns R into a topological ring. The I-adic topology is Hausdorff if and only if the intersection of all powers of I is the zero ideal. The p-adic topology on the integers is an example of an I-adic topology. Completion. Every topological ring is a topological group and hence a uniform space in a natural manner. One can thus ask whether a given topological ring R is complete. If it is not, then it can be completed. One can find an essentially unique complete topological ring S which contains R as a dense subring such that the given topology on R equals the subspace topology arising from S. The ring S can be constructed as a set of equivalence classes of Cauchy sequences in R. The rings of formal power series and the p-adic integers are most naturally defined as completions of certain topological rings carrying I-adic topologies. Topological fields. Some of the most important examples are also fields F. To have a topological field we should also specify that inversion is continuous, when restricted to F0. See the article on local fields for some examples.